Hello, so in this video, we're going to look at answering question 4 from the mechanics section of the 2022 mechanics paper 3 maths exam for A-level maths. So we're going to answer the A-level 2022 paper 3 mechanics section question 4 question. So let's just go back to question 4 here. So this one here, where we've got a uniform rod AB and it's got a massive M and a length of 2a. So yeah, with these diagrams, I always do like to draw my forces on my diagram just so I can actually see the force diagram, because yeah, this is going to be a question where we're going to need to use forces to help us out. So I'm going to have to refresh my page just because my pen tool won't load up. There we go. Right, now let's go back to full screen mode. There we go. So with this question here, as soon as I see information about a mass and a length and weights, I just want to add some force to my diagram just so I can visualize what's going on. So we've got a uniform rod AB, so this rod on the bottom here has got a massive M. So the way that this works is that your mass, you take the mass to be in your center of mass. So that's what we assume in these questions here. We assume that a rod has its center of mass bang in the middle there. So we're going to take the center of mass there, and we've got a weight going down. Sorry, let me try and do this a bit more vertical. So you've got a weight going down there, and that's going to be capital mg. So that's your weight going down there. So mass times by acceleration is your force going downwards. Okay, so you got that. And we got a length of 2a. So just bear in mind that AB is 2a. So just write a note here that AB is equal to 2a. So this means that this midpoint there, if we call this, well, they call that C there. If we call this midpoint there, I'll call it P for midpoint, as in P for point. So we know that this A to P is going to be A, and we know that P to B is going to be A as well. So we'll just make a note of that because that's in the middle of the length. Now we know also that we've got a mass of 2m attached to the rod at point C. Okay, so we've got a mass going down there of 2m. So we've got a weight going down there of 2mg vertically downwards. So remember, our weights are going vertically downwards, so our weights always go vertically downwards. So we have 2mg going down there. And again, we'll just make a note here. The AC is 1.5a. Okay, so then what else we got? So we got the rod resting at its end A on a rough horizontal ground. Okay, so we've got friction. So when we see this word rough, it means you got friction. So we've got friction on the ground here. So which direction is the friction going to act? And in fact, well, that's actually part of the question. Which direction is it going to act? I mean, they tell us in the question it's going to be right, but why would the friction be going to the right direction? So let's think about our force diagram. So we've got our two vertical forces going down here, the mg. Sorry, let me get my cursor back. So the mg going down there, the 2mg going down there. These are vertical forces. Let's think about the horizontal forces that we have. So we've got no other vertical. Well, I mean, we've got this as we can see in the next part of the sentence. So the rod is held in equilibrium at an angle theta to the ground by a light string that is attached to the rod at the end of the rod at B. So we got this rod here which is pulling us upwards. So there's going to be this string. Sorry, this is a string here. So you got this string here at the end. So this string here, and that's pulling us upwards. And there's going to be tension there. So just call the tension, the force in the string, the tension T. So what we notice is that we can take components of this tension force here, can't we? So what we can do is we can just kind of make like a right angle triangle like this. We can split the force into components. So you've got this horizontal component here going to the left, and we've got this vertical component going upwards. So the only vertical forces we have here is this component of tension. So this component of tension going upwards, this downwards 2mg, this downwards mg. So those are our vertical forces. Now let's think about our horizontal forces. So we've got friction, which is obviously a horizontal force. So friction is acting on the surface on the ground horizontally. The only other horizontal force we've got is this component of tension. So this component of tension here going to the left there. So the answer to part A, why is the friction on the ground acting on the rod going to the right here? Why is the friction going in this direction, and it's because we know that the rod is held in equilibrium, and the only other horizontal force is this component of tension going to the left. So what we would say with this one is that we have so the component of tension in the string acting on the rod, so horizontal component, so the horizontal component of tension in the string is going left. So again, as we can see in the rod, we've got a component of tension horizontally going to the left. And since the rod is in equilibrium, sorry, let me just want to write my words as neat as possible. So it's going to the left, going to the left. And since since rod is in equilibrium, sorry, just write the B again. So since the rod is in equilibrium, this means that friction must be going to the right, so must be going right. So yeah, hopefully that makes sense. So again, we've got friction, which is a horizontal force. It's a horizontal force. We've got tension. We've got a component of tension which is horizontal, which is going to the left. So in order for the rod to be in equilibrium and not move, we need this friction to be going to the right to counteract this component of tension there. So the horizontal component of tension, so I'll just make my O neater just so you can clearly see that this is an O. So horizontal component of tension is going of the string. So I'll just write oh no, my my page is frozen again. Sorry, give me 1 second. We'll give my laptop 1 second, please. Come on. I really don't need to deal with this today. Right, there we go. Right. So the horizontal component of tension in the string is going left. And since the rod is in equilibrium, this means the friction must be going to the right to counteract the component of tension going to the left. So hopefully that all makes sense. So we'll go to the next part. So the tension in the string is T, so we've called that T there, luckily there. So what we want to do now is show that T is equal to mg times cos theta. Okay, right. So the way that we're going to have to do this, I mean, the problem with we could resolve forces, so we could do horizontal forces to the right equals horizontal force to the left, and then we could do vertical forces downwards equals vertical forces upwards. We could do that. The problem we've got with that is that we don't know the friction, so we don't know what F is. We don't know what the tension is as well. So we can't really, and also I forgot another force as well. Sorry, I've also forgot this force here. We've got a reaction force here on the ground, don't we? So I call this R here. So we've got the reaction force, the normal reaction force acting at A onto the rod. So because we've got three unknown forces, resolving forces, I mean, it's going to help us probably for part C of the question, but it's not really going to help us to get the tension because we've got these two unknown forces acting at A. So the trick to deal with this, to get rid of the to basically ignore this reaction force and this unknown reaction force and this unknown friction. So the thing we want to do is take moments about A. So the thing that the special thing about taking moments is that it actually eliminates unknown forces because we can take moments about a point on the rod where we have unknown forces. So the idea with this kind of question, where we have an unknown friction and an unknown reaction force at a point, is we can take moments about that point because then we don't have to worry about these unknown forces F and R. So that's what we're going to do with this question. So we're going to take moments. So let's just write this down here. So part B of the question is to take moments. So take moments about the point where we have two unknown forces, and then that's going to help us out. So take moments about point A on the ground, because then we don't have to worry about we don't have to worry about these forces F and R. And the reason why, again, is because remember our formula for moments. So moment is equal to, so moment equals force times by perpendicular distance. So that's the formula we need to know. Sorry, I spelled perpendicular wrong. Perpendicular distance. And obviously the distance from A, the position A to the forces R and F is just 0 because the forces are literally acting at A there anyway. So the distance will be 0. So the moment about A is 0. So you don't have to worry about these forces. So that's the reason why we're taking moments specifically at A. So we're going to do that now. So take moments about A. So because it's in equilibrium, that means that our anti-clockwise moments, so anti-clockwise moments, are equal to our clockwise moments, because obviously, again, the rod's in equilibrium. So let's think about, let's start with our anti-clockwise moments. Let's look at what we have as our anti-clockwise moments. Okay, so let's look at the diagram. So we're fixed at this point A, that's where we're taking moments about. Now, what's going around, what forces are going around anti-clockwise, perpendicular to the rod? Again, it's really important that we remember that moments is the perpendicular force times by the distance. So the force and the distance must be perpendicular to each other. So going around anti-clockwise, so anti-clockwise, what's going around anti-clockwise about this point A? So it's this tension, isn't it? So if we think about it, we've got this rod, we're fixed to the point A, and then we've got this rod, and then we've got this tension which is trying to pull us around anti-clockwise. And luckily, the tension is actually perpendicular. So you've got this right angle here. So it's perpendicular to the distance, it's perpendicular to the rod. So our anti-clockwise moment is just going to be the force, which is the tension, and then times by the distance, this perpendicular distance of the force, which is just the length of the rod AB, which is 2A. So it's going to be T times by 2A, so 2AT. Okay, now let's think about our clockwise moments now. So let's go to our clockwise moments. So clockwise moments. So with this one, we just got to be a little bit careful. So now we're thinking about the things going around clockwise. I'll do this in a different color now. So now everything going around clockwise about this point A. There's two forces in it. So it's this mg going down there and this 2mg going down there. We got to be careful because this force is not perpendicular to the rod. So and that force as well is not perpendicular. So that angle there, these two green angles are not right angles. So therefore, we have to take the perpendicular component of those two forces. So what we're going to have to do, so let's I'm actually just going to zoom in, I think. Let me just zoom in. So we're going to take perpendicular components of the forces. So we're going to split our two weights into components. We're going to do like a little right angle triangle like this. So remember how this works. So just zoom in again. So the way that this works is that we have the angle theta there. So that's an angle of theta because that's the same as this angle there, and an angle of theta there. If you're not sure why this is theta, I'll go for in a minute why that is theta, but just bear with me for a second. So if you're happy with that, we know that that's an angle of theta there. So angle of theta there, angle of theta there, and then we can take components. So the component perpendicular to the rod AB, so this kind of adjacent component to the theta. So with this one, it's going to be 2mg cos theta there, and with this one here, it's going to be mg cos theta there. So that's the component perpendicular to the rod, because now this makes a right angle. Let me try and yes, so this makes a right angle there, that makes a right angle there with this perpendicular component. Let me just rub this right angle out and these dots up there as well. Okay, so now then we can write down our moments. So the distance between the first force, the first perpendicular force was this mg cos theta, and the distance from A to P, the midpoint, was A, wasn't it, as we can see down there. So it's going to be A times by mg cos theta. So A times by mg cos theta, and then plus our second moment, so this one here, so the A to C distance, which was 1.5a, and then times by the component, the perpendicular component, so 2mg cos theta, plus 1.5a, 5a times 2mg cos theta. Okay, that's great. So now then we can put our anti-clockwise moments equal to our clockwise moments. So we're going to get 2at is equal to amg cos theta, and then plus, so 1.5 times a times 2, well, double 1.5 is 3, so that's going to be a 3amg cos theta. And actually what we're going to get is we're going to get 2at is equal to, so 1a mg cos theta plus 3a mg cos theta, that's going to be 4a mg cos theta. We can actually just cancel out the a there and the a there, divide both sides by 2. We get t is equal to 2 mg cos theta, and that is exactly what the question required of us. So the question wanted to show that t was equal to that, so we just use moments to do that question there. I'm also going to again just go through, in case you're unaware, why this angle there is theta. So let me get my cursor back. So this angle there, why these two angles there are theta, just in case you don't know why. I'm just going to go to a whiteboard to explain this. So let's say again you've got like a rod like this at an angle of theta, and then you've got like some weight going down there, so some vertical weight going down there. So what is this angle there going to be? So the idea is that this is 90 degrees there, because you've got a perpendicular line going through the base there, this horizontal base perpendicular to this vertical weight. So that's 90. Angles in a triangle add up to 180. So that's going to be, this angle here is going to be 180 take away 90 take away theta. So that's going to be 90 minus theta inside there. Now, this component here, this component going down there, is perpendicular to the rod, this rod here. So that's 90 degrees there. So this missing angle inside there is going to be 90 take away 90 minus theta, which is equal to just positive theta, because 90 take away 90 is just 0. Minus theta is positive theta. So that's why this angle inside there is theta. So hopefully that explains that, just in case you forgot why that was true. But anyway, going back to the question, so we've done part A, and we're going to move on to part C now. So we're given that cos theta is 3/5. So now we've got to show that the magnitude of the vertical force exerted by the ground on the rod at A is 57 mg/25. So the magnitude of the vertical force exerted on the ground, so it's this R here, this this reaction force here is basically what we want to find in part C. So the vertical force exerted by the ground on the rod. So we want to find with this part, so find the reaction force. Okay, so how will we do this? So the first thing is to use this piece of information here that cos theta is 3/5. So the way that I'm going to do this is I'm just going to draw a triangle. This is the way that I like to do this. So you've got an angle of theta there. We've got this rod going upwards, this inclined rod. Now remember what cos is. Cos is adjacent over hypotenuse. So we've got here adjacent over hypotenuse. So the 3, we can call the adjacent side 3. We can call the hypotenuse 5. So what's our opposite side going to be? So this is just going to be the square root of 5 squared take away 3 squared using Pythagoras. And if you work that out, you should get 4. So we know that sine theta must be 4 opposite over hypotenuse, so 4/5. So we know that sine theta is 4/5, and we know that cos theta is 3/5 because the question tells us so. Okay, so now that's going to be helpful, because now we can actually calculate what the tension actually is. So we know that the tension was 2 mg cos theta. So this is part C now. So part C. So T is 2 mg cos theta, as we got here. But we know that cos theta is 3/5, as the question says there. So it's 3/5. So you just plug that into the result. So it's going to be 2 mg times by 3 over 5. And that's going to be 6 over 5 mg. So that's our tension. So let's go back to our diagram and add some extra data in. So that T is going to be 6 over 5 mg. So then we want to find the reaction force. So now we can just do balancing forces. We can just do balancing vertical forces. Remember, we want to find R. This is what we want to find in part C of the question. We've got to find the R. So forces going upwards equals forces going downwards. We just got to resolve the vertical forces because we know the tension, we know the two weights going downwards. We just want to find the upwards R force. So with this question, we're just going to resolve the forces vertically. So resolve forces vertically. So again, everything's in equal. The rod's in equilibrium. So forces going upwards equals forces going downwards. So forces upwards equals forces. Sorry, I spelled that wrong. Forces downwards. Forces downwards. Okay, so upwards forces. It's going to be the R, and then plus this component of tension here. So plus this this component of tension. So what would this component of tension be? So let's try and draw like a diagram over here. So we've got this tension going upwards here, which is 6 over 5 mg, and we want to try and find this vertical upwards component. So what would this upwards component be? So the key thing to remember with this is if we try and we just draw like a parallel line here, parallel to the base of the horizontal, the horizontal ground at the bottom. So using alternate angles, we know, and I'll do this in a different color, I'll do it in purple. So using alternate angles, so Z angles basically, we know that this angle there is going to be theta. So that's theta inside there. So what do we have? So we know that we've got a right angle there, perpendicular to the rod. So the rod is perpendicular to tension. So that means that this angle inside there is going to be, I mean, if we try and zoom in as much as we can. So we've got 90 degrees. Again, I've made a bit of a mess of this, but let's try and explain this. So we've got a right angle here. We've got theta, which is part of this right angle. So it's part of this right angle. So this angle there is going to be 90, take away theta. And so this angle up there is going to be theta. So that angle there is actually theta. So what would this adjacent component be? So this adjacent component of the tension be next to the theta. So remember, adjacent over hypotenuse is cos. Hypotenuse there is 6 over 5 mg. So this is going to be, so this component here is going to be 6 over 5 mg cos theta. And this one down here is obviously going to be 6 over 5 mg sine theta. Because remember, sine is opposite over hypotenuse. So your opposite to the theta, this opposite component, opposite to the theta will be 6 over 5 mg sine theta instead. Okay, so now then we know the upwards components of the forces on our rod is R, and then plus this 6 over 5 mg cos theta. So upwards forces, it's going to be the reaction force which you want to find, and then plus this 6 over 5 mg cos theta. And then that's going to be equal to our downwards forces. So what forces do we have going vertically downwards? So it's just the mg going down there, just that mg there, and then plus this other 2 mg going down there as well. Okay, so mg plus 2 mg. Okay, great. So then now we've got R plus, so 6 over 5 times by mg. And then remember again that cos theta is equal to 3 over 5. We'll just plug that in again. So 3 over 5. And then that's going to be equal to, again, mg plus 2 mg. So 3 mg. So therefore, the reaction force is going to be 3 mg take away this 6 over 5 mg 3 times by 3 over 5. So what's that going to be? So 6 times 3, that's going to give us 18. And then 5 times 5 is going to give us 25. And then just times by mg there. Okay, so that's that. And then now we can just simplify our result. So 3 is the same as 75 over 25. So 75 over 25 mg, take away 18 over 25 mg. And then we've got a common denominator, 25. 75 take away 18, that's going to give us 57. So 57 over 25 mg, that's going to be our reaction force. And that is exactly what we had to get. So we had to show that the reaction force is 57 mg over 25, and we just done that there. Perfect. So that's the part C of the question done. And then the next part, the final part, so the coefficient of friction between the rod and the ground is mu. So given that the rod is in limiting equilibrium, show that mu is equal to 8 over 19. So this term here, limiting equilibrium, what that means is that friction is the maximum possible value that it can be. So let's just make a note of this just to remind ourselves. So this term here, limiting equilibrium, just means that friction is at its max value. So in other words, so equivalently, it means that friction is equal to mu times r. So remember, technically, the formula for friction is less than or equal to mu times r. That's technically the technical formula, because obviously, if you think about it, if you've got like a block of material on a rough surface, if you keep on increasing the force that you push it with, there's going to be a point when the block starts to move. So let me go to whiteboard to try and explain this properly, just in case you need this explanation. So imagine you've got a surface like this, you've got a block, and you're going to push it a little bit. So you're going to push it to the right a little bit, but it's not moving. So you're going to push it a little bit more, still not moving, push it a little bit more, still not moving. So the more you push it, the bigger the friction gets. So friction balances your force until you push it hard enough so that you get to a maximum friction. So let's say that this is your max friction there. So let's say that this force here is your max friction. And then once you push the block to the right with your max friction, then it's still not moving because it's equal to the maximum friction. But then when you push it more, so greater than, so you're going to push the block to the right with a force greater than max friction. Obviously this is the maximum friction, so your friction can't get bigger than this maximum. Now the block's going to move to the right because you pushed it. You pushed it with a force greater than your maximum friction. But if you push the block with the force less than your maximum friction, your friction isn't equal to this maximum friction. Your friction mirrors the force that you push it with. If you push the block to the right with a force less than your maximum. So that's why the formula is friction is less than or equal to mu times r. But when we hear this term limiting equilibrium, it just means that the friction is at its maximum. So the friction acting on the rod or on the block in this diagram here, but in our exam question, we're talking about the rod. So the friction acting on the ground down here is at its maximum value. So friction is equal to mu times r. Okay, so now we're going to try and show that mu is 8 over 19. Let's have a go at this. So part C, I'll do this in a different color. Let's do it in just do it in red. Okay, so part D. So we know that friction is equal to mu times r, and mu is equal to so mu we don't know, we're trying to find mu, but we know that the reaction force is this 57 over 25 mg, so we know that. Now then, is there a way that we can actually find a value for this friction? And yes, there is. So remember that the rod is in equilibrium, so the rod A to B is in equilibrium. So let's just, bear in mind that the rod is in equilibrium. So remember that means that the component of tension, so this component of tension here, must be equal to the friction. So it's in limiting equilibrium. So this friction going to the right must equal this component of tension going to the left, because these are the horizontal forces. So we're going back to part A of the question, really. So horizontal component of tension in the string is going to the left. And since the rod is in equilibrium, this means friction is going to the right. So friction must be equal to this component, this horizontal component. So horizontal component of tension. Component of tension. Okay, so that means that the friction is going to be equal to this here that we calculated in the previous part. So it's going to be equal to 6/5 mg sine theta. Okay, so we know from the diagram that friction is equal to 6/5 mg sine theta. And from our calculation back here, we know that sine theta is 4/5. So sine theta is 4/5. So we've got 6/5 mg times by 4/5 is our friction. Okay, so that means if we just simplify this, so 6 times 4 is 24, 5 times 5 is 25 mg. So therefore, that means that the friction is equal to mu times the reaction force. So 24/25 mg to our friction is equal to mu times by the reaction force here, this 57/25 mg. So 57/25 mg. So now what we can do is just cancel out the m's on both sides, divide both sides by m, they cancel out. The g's as well, they cancel out. And then what we can just do is divide both sides by 57/25. So mu is going to be equal to 24/25 divided by 57/25. So keep, change, flip, 24/25, change to a time sign, flip the second fraction. The 57 is going to cancel out. So you get 24/57. We can actually divide both numbers by 3. 24 divided by 3 is 8, and 57 divided by 3 is 19. And there we go. We get that mu is equal to 8/19, which is exactly the same as we had to get here. Okay, great. Yeah, so that'll be how we answer this question. So quite a tricky one. These questions where we got to do like, friction, we got to involve friction and rough surfaces, and also do some moments. So these kind of rod questions, they're always difficult questions. It's just a case of remembering that if you do get a rod inclined on like an inclined surface, generally speaking, you're going to have to use moments, and you're going to take moments where the friction is acting and where the reaction force is acting. So generally with these questions, you're going to take moments about the point where you've got two unknown forces. So the reaction force, which you don't know, the friction force you don't know. You want to take moments about that force. Remember that moment equals force times perpendicular distance. So your force must be perpendicular to your distance on the rod. So just make sure you take a force which is the component of the force perpendicular to the rod. Do your moments, and then just proceed with the rest of the question to answer the rest of the to find the rest of the forces, and also to find the coefficient of friction. So yeah, that was how we answered that question. But any questions, just let me know in the comments